All right, how'd you do on this problem? Feel good about it or not? If you don't feel good about it, it's okay, we can get better. So here again is the problem. We're trying to come up with an exponential model for population growth. Why? Because population often does grow approximately exponentially. Not always, but oftentimes. And we're ultimately trying to find something called the doubling time. We're going to have to solve for a time, an unknown time that's in an exponent, and therefore we'll need logarithms. So 40 million people in the year 2000 at t equals 0, 48 million people in the year 2010. Find the population in the year 2020 after you find an expression for the population as a function of t, and then find the doubling time. Okay, so I think I got that stuff memorized here. Set it up. Let t be time in years since the year 2000. Do you have to write that down, that kind of thing down in your homework? No, but I think it's a good idea, just for clarity's sake in your own mind, to write down what the variables mean, including units. As far as the population goes, you could call it y, you could call it p for population if you like. So that's the population. And like I suggested before you started the problem, since the numbers are so big, instead of using units of people, use units of millions of people. Million people. The idea is that p is a function of t. P equals f of t. We want to first figure out what that function is. Okay, we can use the form a times b to the t if we like to, or we can use the form a times e to the kt. Either way is okay. They both have their pluses and their minuses. When you write it as an arbitrary b that you have to solve for, it's easier to interpret the population growth as a percent rate of change per year, per unit time. K is a continuous percent rate of change, but because it's continuous, it's a little harder to interpret. However, this does have the benefit of being nicer for calculus, you might say, because it's easier to take the derivative of when we get to taking derivatives. I will solve for it in this form first, but then I will also convert it to the other form. A in both cases is the same. The A is the initial population, because when you plug in t equals 0, you're going to get b to the 0 or e to the 0, which is 1 in either case. A times 1 is A. A is the initial population. You could also call that P sub 0 if you like. That's a common thing to do. The initial population, actually, we already know it's 40 million, or just 40 if our units are a million people. P0 is the function value at time 0. That's given to be 40 million. Let's figure out the K again. We know that in the year 2010, the population was 48 million. 2010 is 10 years after the year 2000. We aren't worried about the exact moment when t is 0. Is it at the beginning of the year 2000 or at the end or in the middle? It doesn't matter. We're being approximate here. Plug in t equals 10. I'm going to go ahead and use the E form. Go ahead and plug in the initial population of 40 million. And we have to use logarithms here too, actually, because we need to solve for K. Question? Oh, okay. Yeah, it's not completely clear. I'm taking it to be t equals 0 at some point in the year 2000 and t equals 10 to be 10 years later. It's understandable that you did that, but I think that's what the book intends. Think of, if you want, you can imagine it to be January 1st in both years. Then they would be 10 years apart. Need to solve for K. Logarithms are how you solve for unknowns in exponents of exponential functions. Take the log of both sides. Since it's base E here, I might as well take natural log of both sides. If I do it to one side, I have to do it to the other. I could have divided by 40 first, and that might have been simpler. But I also can do it this way. It doesn't really matter. In fact, I'll show you that you get the same answer in the end. However, this way is a little trickier because you got to use a couple properties of logarithms. First, there's the fact that the log of a product is the sum of the logs. You got 40 times e to the 10k here. That's natural log of 40 plus natural log of e to the 10k. That's a property of logarithms that, again, was something that you should have learned in pre-calculus. You were tested on with the placement exam and the skills test. We are going to look perhaps at the proof of this, maybe even in class today. I do it in the lectures as well. I don't know that it's lecture 5, but eventually I do. Why does that work? At the moment, we're just trusting it. You can't really simplify that much. Not with an ln, at least. If it was an log for common logarithm, you could a bit. Here, this can be simplified. What does it simplify to? 10k, yeah. Natural log of x and e to the x are inverse functions. That's how the natural logarithm is defined in the first place. I'll talk more about that in a bit as well. So when you plug a quantity into the exponential function, e to the x, and then take that quantity and plug it into the natural logarithm, you get back what you started with, 10k. The goal is to solve for k. This is a linear equation in k. Yeah, you got these complicated looking things in there, natural log of 48, natural log of 40. They're just numbers. Just treat them as numbers. Subtract natural log of 40 from both sides. It'll cancel on the right. You'll have natural log of 48 minus natural log of 40 on the left equals 10k. Now divide both sides by 10. Cancel the 10s on the right there. In the end, you get k is natural log of 48 minus natural log of 40 divided by 10. Now, if you divided by 40 right away, your answer probably looks different. There's another property of logarithms that says, well, the log of a quotient, a fraction, is the difference of the logs. Here we have the difference of two logs. That's equal to the log of the quotient, 48 over 40, as one logarithm. 48 over 40 can be reduced. It's the same as 6/5, which is 1.2. So if you got natural log of 1.2, you did it right as well, over 10. If we had divided by 40 right away, we would have gotten the same answer. Divide both sides by 40. 48 over 40 equals e to the 10k. This simplifies again to 6/5, or 1.2. Now take the natural log of both sides. Natural log of 6/5 is natural log of e to the 10k is 10k. And once again, divide both sides by 10, and you'll end up with the same answer. There's the exact form of the value of k. You should be able to write answers in exact form, not just approximations. And in fact, it's a good idea to try, if you can, to leave it in symbolic exact form until the very end. Because if you round too soon, the errors build up, they propagate and get worse and worse as you keep rounding, as you keep doing more calculations. So it is a good practice to try to make things in exact form and only round, use your calculator at the very end. I mean, you should be able to do it symbolically anyway. K is about 0.01823. As a percent, that's 1.823%. That's a continuous annual growth rate. It's a bit tricky to interpret. I will try to interpret it in a few minutes. Before we solve for the doubling time, let's also figure out this form of the answer. The A is the same. It's still P sub 0. The B will be different. The B can be found, though, because by a property of exponents, this thing is equal to, well, a times e to the k quantity to the t. And these two things are going to match exactly when the b is equal to e to the k. So if you know k, which we just figured out, b is going to be e to the k, e to the natural log of 1.2 divided by 10, which you can plug in your calculator, or you can also do a little simplification first. You can use another property of exponents to write, well, this is maybe less simple looking, but it emphasizes something. We can now write this, because that's a property of exponents, that when you've got something like this, you can multiply the exponents. And when you multiply natural log of 1.2 and 1/10, it's the same as this fraction here. And now e to the natural log of 1.2 and the, well, they cancel out because they're inverse functions. So you're left with natural log, or 1.2 to the 1/10 power, or the 10th root of 1.2. Whatever that happens to be, I'll solve for it in a second here. One thing this emphasizes actually is that over a 10-year period, the population grows by 20% over a 10-year period. Because of the 1.2. 1.2 is 1 plus 0.2. It's a 20% growth over the 10-year period, which actually makes sense if you think about it. 48 is 20% bigger than 40. Why? Well, 20% of 40 is 8. 40 plus 8 is 48. Yeah, the population grew by 20% over 10 years. But now we want the growth factor over 1 year. That's this root here, which you can do as a 1/10 power, 1.2 to the 0.1. It's about 1.0184. 1 plus 0.0184. That means the actual annual growth rate is approximately 1.84. Yeah, and if you round it, it's 840, in fact, 840%. A little bit bigger than this continuous growth rate. Realize this actual annual growth rate is how much the population actually grows every year by that percent. Let's illustrate this by thinking about it a little bit more. So it starts out in the year 2000 with 40 million people. What does it mean to grow by about 1.84%? Well, what's 1.84% of that? 0.0184 is what to multiply it by. That's 0.736. In other words, since the units are millions of people, that's 0.736 million people, which would be 736,000 people. Then add that on to the original population. That's going to be the approximate population in millions in the year 2001. I could have done that just by multiplying by 1.0184 instead of doing 2 steps. And in fact, now every year, if the population really does grow by 1.84%, I can just keep multiplying by that number. There's the approximate population in the year 2002, 2003, 2004, 2005, 2006, 2007, and 2008. Oh, that was the wrong drum roll. Sorry, I meant to go to 2010. 2009, here we go. And 2010, yeah, 48 million. Off a little bit because I rounded. So if the population truly grows by 1.84% every year, then those are the populations in all the intermediate years. Of course, it's not going to do that exactly. These are always approximations. Does that make sense? All right, let's solve for the doubling time. And then let's also try to interpret this continuous annual growth rate. What does it mean? It's a bit subtle. For the doubling time, By the way, on your participation, when you take your pictures, I want to see both your work that you were trying before I showed you my work here, and if you're taking notes, my work as well. That's not the word doubling. Doubling. Oh, okay. I thought that was a D. D-O-U-B. This is B-L here. Doubling time. Call it capital T sub 2. Just a shorthand notation for doubling time. What is the doubling time? How do you, somebody tell me how I would find the doubling time. Did you know what to do? Set what equal to 2? The function? You're on a right track, but it's still not quite right. Yeah, 2 times the initial value, which is 40. So, I mean, I guess I haven't actually written the function anywhere. The approximate function that we're using for the population, which was supposed to be the answer to the first question, P equals f of t is approximately 40 million times e to the 0.01823 t. Yeah, I'd have to double 40 to write 80, which does effectively, if you divide both sides by 40, make a 2 on the other side, as long as you don't have the 40 again. Does that make sense? We want to set this equal to 80. We want to double the 40. But then I could divide both sides by 2, and then just the exponential part will equal 2. So what you said was correct after that point. So that's what I want. 80 is going to be f of t2. Why 80? Because 80 is twice 40. Divide both sides by 40, and you get 2 equals e to the 0.01823 t. Now take the log of both sides. ln2 equals ln of this, but because it's base e, those are inverse functions, and you get just 0.01823 t. Well, I should call this t2, sorry. t2. Now divide both sides by 0.01823. t2, the doubling time, is natural log of 2 divided by 0.01823. And in fact, in general, when you write your function with e, the doubling time will be natural log of 2 divided by whatever the k is. This generalizes. So we get natural log of 2 divided by 0.01823. It's about 38 years. Close enough to call it 38 years. So we would expect it to reach 80 million people 38 years after the year 2000 in 2038. Will that happen? Probably not, right? You may have heard that birth rates are slowing over time. People are having fewer and fewer babies. That's occurring in pretty much every country in the world. So probably the growth rate, this 1.823%, whether you think of it as a continuous growth rate or an actual growth rate, is going to get smaller over time. It's not really going to be constant. And which means it's going to take longer to get to 80 million people than 38 years. Of course, that also ignores things like immigration and stuff, which can affect things as well. So this was the actual annual growth rate. This is a continuous annual growth rate. I mentioned that verbally, but I didn't write that down. Continuous annual growth rate. But what does the continuous annual growth rate mean? That's pretty tricky, but let me explain it to you now. It's probably better to take another example because it'll be more clear with another example. It's going to be more clear the bigger the growth rate is. Let's pretend we're with an example where the actual growth rate is 50% every year. New example. Actual growth rate is 50% per year. By the way, I forgot to mention with the doubling time, that's if you truly have exponential growth, that will stay constant. It doesn't matter what the starting population is. It doesn't matter what the time is. The amount of time it takes in exponential growth to double is constant. So if we're in a situation where the actual growth rate is 50% per year, we could write our function, say for a population, as p sub 0, don't use e, instead use 1.5. 1.5 to the t. That represents 50% growth every year. Think about it. If I pretend P0 is, say, 1,000 to start with, then after time, 1 year, we're up to t equals 1, we'd multiply by 1.5, we're up to a population of 1,500. 50% of 1,000 is 500. 1,000 plus 500 is 1,500. It grew by 50%. Multiply by 1.5 again, which I can just do by hitting answer again, or enter again. I'm up to 2,250. That's also 50% growth because 750 is half of 1,500. And 2,250 is 1,500 plus 750. What's it going to be the next year? Take 15 seconds to see if you can figure it out. Can you multiply by 1.5 in your head, or maybe multiply by 0.5 first and then add this? That sounds good to me. Yeah, 2,250 times 0.5, half of this is 1,125. Add that to this, you'll get 3,375. That's 50% growth. That's a pretty high growth rate. If that was your money growing in a bank account somewhere, that would be unbelievable. Of course, no bank accounts do that. Not even the stock market does that. Bitcoin maybe, yeah, or GameStop, or well, not so much anymore. Yeah. Of course, the stock market and Bitcoin don't just go up, they go up and down. You know that, right? They don't always go up. You're looking for average rates of growth over time with those things. What would the corresponding continuous rate be? So the B equals e to the k, like I already mentioned. Therefore, k is natural log of b. Natural log of 1.5. The b, by the way, is not a growth rate. Does that make sense? It's 1.5. That's not 50%. That's like 150%. It's a growth factor. Better to call b a growth factor. You keep multiplying by it instead of a growth rate. But if you subtract 1 from it to get 0.5, 0.5 is 50%. That's 50% growth as a rate of growth. Anyway, what is ln of 1.5? It's about 0.4. 0.405465, let's say. 40.5465% is the continuous growth rate. How do you interpret that? Here's how. Think about it graphically. And you should be able to do this interpretation on the first exam, by the way. If I graph this function as a function of time, P0 is the initial population at time 0. That's a P sub 0 there. This is exponential growth, and it's pretty fast exponential growth. After 1 unit of time, say right about here, the population is 50% higher than it was to start with. It's 1.5 times the initial population. At t equals 2, we saw from the calculator that the population would be 2.25 times the initial population. At t equals 3, what we see 3.375 times the initial population. This is concave up, it's growing faster and faster. The derivative, the rate of change, is getting higher and higher as well. The slope is getting higher and higher. It's curved, it's not straight, but what would happen if we did approximate this with a straight line at any point, like the starting time? What would it mean to approximate this with a straight line? Well, there's lots of ways you could try to approximate it with a straight line. You could just draw a line about like that and then say, hey, I'm approximating with a straight line. However, with calculus, we want to use a special line that's not the best approximation overall over the interval, but is certainly the best approximation near this point that I just circled. It's called a tangent line to the curve. Looks about like that. It intuitively, at least with circles, you imagine tangents just barely touching the circle. And in a sense, it's just barely touching this curve here at this point, not literally crossing it. That's not the best way to interpret it when you're not dealing with circles. It's better to interpret it as what the curve looks like more and more as you get closer and closer to that point. In fact, in a minute or two here, I'm going to show you Mathematica to help us illustrate this and understand it better. That's called the tangent line. Tangent line to P equals f of t at t equals 0. Doesn't approximate the curve over the entire interval as well as possible, but again, it does approximate the curve as good as possible near t equals 0. It gets better and better the closer you get to 0. Here's a question. How much does the tangent line grow over the first year? Well, we'd have to figure out what that tangent line is, wouldn't we? Like, what's its slope? Its intercept is p0, but what's its slope? Okay, I'm going to show you a little calculus here. I'm not going to explain it. So here's a little preview of stuff you need to know for exam 2. This is not exam 1 stuff, but I'm going to go ahead and do it here today anyway. I'm going to take the derivative of this thing, of this function here. You can write the derivative in a couple ways. You can write it like that, as if it's a fraction. And when you look at this fraction, you say dp dt. Don't say dp divided by dt, even though we will sometimes pretend it's a division. Calculus gets weird. There are lots of what I call convenient fictions in calculus, or conceptual fictions. Things where you pretend it's one way, but it's really not. Why? Because it's actually helpful. That's why. Maybe if you're in physics especially, maybe this is something that's really confusing to you. Is that thing a fraction or not? Technically, it's not. But it doesn't hurt to pretend it is sometimes, and that can even give you some insight sometimes, and we'll talk more about that as time goes on here. That's a symbol for the derivative. If we give the function a name, if we call it f of t, and it also equals this here, that's also f of t, same function in a different form. We also write the derivative what's called prime notation, f prime of t. And for this example, the derivative turns out to be, well, you can write it in one of two ways. If you think about the function this way, you can write it as p0 times the natural log of b, which is the natural log of 1.5, times b to the t, which is 1.5 to the t. If we use the e representation, base e, instead of an extra factor of natural log of 1.5, we get an extra factor of k. You're just trusting me here. I'm not really explaining this. You don't need to know how to do this for exam 1. Okay, fine. What does it mean? What it gives you is the slope of the tangent line at any value of t. That's what it gives you. That's what it means. In particular, the slope of the tangent line when t equals 0 can be found out by plugging in t equals 0 into this function, this derivative function. Its notation can be written a couple different ways as well. If I use this dp dt notation, I can emphasize plugging in t equals 0 by putting a vertical line here and then a t equals 0 down there. If I use function notation, I can just plug in t equals 0 like that. Plug in t equals 0, you'll get p0 natural log of 1.5, or that's the same as p0 times k. Remember, k does equal natural log of b. It equals natural log of 1.5. So these are really the same thing. These are equal. And this is approximately, based on what I did up here, approximately 0.405465 times p0. That's the slope of this tangent line. It does depend on what p0 is. Okay, if I wanted a particular number, I could plug in whatever p0 happens to be. Pretend it's 1,000, you plug in 1,000. Maybe we should do that. Just to make it a little simpler seeming. Say p0 is 1,000. Then you get this thing times 1,000, which would be 405.465. That's the slope of this red line. So what does that tell you? That does tell you can find the equation of the line to figure out this change right here, this delta p right there. But you actually don't have to figure out the equation of the line. Does anybody think they see what I'm getting at here? You can figure out this thing. Look where I'm pointing right here. Delta p, that length, that change in the population, that can be figured out with the equation of this red line or without it. There's a way to do it without finding the equation of the line. Anybody think they know? Sub what? I'm sorry, I can't quite hear. Oh, yeah, that's a good thing to try. So you said SOHCAHTOA. Okay, so you're thinking trigonometry or the Pythagorean theorem, because we do have a right triangle here. That is a good thought. And certainly the base has length 1. We'd have to figure out the angle, though, or we'd have to figure out the hypotenuse. That's not so clear. Here's a way to do it. The slope, remember, is rise over run. But wait a minute, we really want the rise. Delta p is the rise. If the slope is rise over run, in this case, delta p divided by delta t, then the rise, delta p, would be the slope times delta t. Delta p is not a literal distance, but if I pretend it was a distance, it's distance equals rate times time. Hey, our key equation from lecture 1, right? The key equation for everything I mentioned in lecture 1. Of course, p is not a distance, it's a population, but it's a similar idea. The change in this quantity is the rate of change with respect to time times the amount of time elapsed. So in this case, that would be 405.465 times what's the time elapsed? It's just 1 times 1. This would be, say, if this is a population and say millions of people, this would be millions of people per year, say, and this thing would be in years, and the years would cancel. You'd still get the same number, but it would have different units, 405.465 million people. Oh, well, that's a lot of million. That's a lot of people. Okay. That would be, yeah, that's like the whole population of the country. Okay, maybe this is related to the entire world here. I'm trying to separate these. These are equal as numbers, but the units are different. The units over here canceled for years. And then if the population started out at 1,000 and it followed the tangent line, the red line, instead of the green curve, that's what we were just talking about there, is the change in the red line, not the green curve. Then it increased from 1,000 to 1,405 million people. It increased by 40.5465%. 40.5465%. That was a very long-winded way of trying to interpret that number, but it probably was necessary if you're really going to understand it. What the continuous growth rate is telling you is that at any moment, how fast the population is changing, and the speed at which the population is changing is measured by the slope of the tangent line when you're talking about rate of change at a moment in time. Say that again. When you're talking about rate of change, how fast is something changing? In this case, a population at a moment in time. At t equals 0. The direction of the curve is in the direction of the tangent line. So how fast it's changing is the slope of the tangent line. And so if the growth stayed linear instead of exponential, it would grow by this much. Now, it's not linear, it is exponential, so it grows by more. The green curve is concave up, it's above the red line. The actual growth is more than that, but the instantaneous or continuous growth rate is the 40.5465%. It's a pretty tricky concept, but we're going to re-emphasize it over and over and over in this class. It's what derivatives are all about, is understanding the relationship between curves and tangent lines and what that implies and what kinds of applications it has. That did take a while, but I think it was worth it. Let me just quickly type something up in Mathematica that's going to illustrate this. I'm not going to really explain the code. I guess this is class 6. For the sake of time, so we can have time for another example. Okay, let's just go ahead and use the particular function that we're dealing with p0 equal to 1,000. And I could use e, but let me go ahead and use the 1.5. So we have this in exact form. There's a way to get this function into Mathematica when p0 is 1,000. Let's go ahead and plot it. There's our graph. Sometimes Mathematica doesn't put the origin where it should be. You can see the origin is actually not at this point. Well, you can force it to be there by doing axes origin arrow 0, 0. Let's confirm the derivative. Once I've plugged the function in, I can type f prime of t to get the derivative. There, that 405.465, that's 1,000 times natural log of 1.5, right? Log of 1.5 in Mathematica actually means natural log. That's pretty confusing. Why not use ln? Did I mention this before? It's because Mathematica was created by a physicist named Stephen Wolfram. And when you get into super advanced physics and math, they actually oftentimes avoid using ln and they write log for natural log, because like the natural log is the best log to use, so why not just call it log? The origin of ln is, and natural log is actually French. I think ln stands for like log natural in French or something. But we English speakers, at least, go back to using just plain log when we actually mean natural log if we do really advanced math. Not always, but oftentimes. And so that's why the person programmed it this way. Let's plot the tangent line in there, in addition to the plot of the function itself. If I put the function inside curly braces and put a comma in here, I can type in the equation of the tangent line as well, approximately. F prime of 0 is the slope, 405.465, 405.465 t, and the y-intercept is 1,000, plus 1,000. So there's the tangent line that I drew by hand. Under the graph of the population function itself, it's the tangent line at t equals 0. And the point on the graph when t is 1 on the blue graph is the actual population up at 1,500. On the orange graph is slightly lower. It would be at 1,405 approximately, is what that point would be. And I can confirm that by plugging in t equals 1 in here. I mean, that'd be easy. You can just do it in your head, actually. You get 1,405 when you plug in t equals 1. Well, let me do something a little bit more fun here, quick. Let's try to understand this visually. And I'm not going to explain what I'm doing here because I don't have time, but just bear with me here. Let's see if this works. Okay, so I'm graphing the same two graphs on a different scale. And this epsilon parameter, I'm letting go down towards 0, and I'm zooming in closer and closer to the graph. Zooming in closer and closer to where t equals 0. And what I'm seeing here, I'll start epsilon bigger. And maybe make this bigger here. Okay, what I'm seeing here now is the two graphs again on a bigger window. If I zoom in to both graphs when t equals 0 and p equals 1,000, I see the tangent line, the orange graph, getting to be a better and better approximation of the blue curve. That's how you should really imagine tangent lines. Not as just barely touching the curve. That only really works with circles. It sort of works here, but you got to be careful because the graphs can do strange things. So it's better just to imagine it as a better and better approximation to the blue curve as you zoom in closer and closer. That's the essence of calculus, right there, of differential calculus. All right, let's do another example. I think doing these individual examples in depth, I think is still valuable, even though it'd be good to see more examples. Because there's a lot of important concepts to try to get across. These are really, really important concepts. I'm emphasizing the most important concepts here. Let's quickly do another problem where it's an exponential decay instead of exponential growth. If you're going into medicine, it is common for drugs in your body to decay exponentially. So number 39 is an example of this. At time t after taking the cough suppressant, hydrocodone by tartrate, the amount A in milligrams remaining in the body is given by this function. 10 times 0.82 to the t. This is in the form A times B to the t, where B now is between 0 and 1, not bigger than 1. When B is between 0 and 1, that's actually exponential decay. And it's really no longer a growth factor, it's a decay factor. Maybe in general, it's better to call it a change factor. Factor implies multiplication. That's why I'm using the word factor. Because after each unit of time goes by, you keep multiplying by 0.82 in this case. So the amount in your body goes down. Is this a perfect model? No. Because how is your body eliminating it? Probably from urination or from perspiration, which don't happen all the time. So this is an approximate model. I mean, your body could be breaking it down, the chemical itself as well is another way it could be going down. So maybe because of that, it's a good approximation. We want to answer, what's the initial amount taken? What percent of the drug leaves the body each hour? How much of the drug is left after 6 hours? And how long until only 1 milligram is left? And maybe that's when it's safe to take another dose or something. That could be the ultimate application. So we're given this function. The amount in milligrams is a function of time in hours is 10 times 0.82 to the t. You could write this without the parentheses around the 0.82, but if you did write it without parentheses, you'd probably want to put a dot in there for multiplication. And it would be understood here that you do the exponentiation first before you multiply, because of an order of operations, exponentiation gets done first. So raise 0.82 to the t power first and then multiply by 10. That's very important. You'll get the wrong answer if you multiply by 10 first. What's the initial amount taken? Again, this is in milligrams, and t is in hours. Plug in t equals 0. It's the A, the 10. Maybe you call it A sub 0 instead of P sub 0. A sub 0, the amount at time 0 is 10 times 0.82 to the 0 power. That's a big 1. 10 times 1 is 10. 10 milligrams. The answer to A. B, what percent of the drug leaves the body each hour? Actually, you should be able to say what that is without even doing any work, just thinking about it. Does anybody think they know the answer to B? 18%, yep. Why? Because 1 minus B, this is the B here, it's a decay factor. 1 minus B would be the percent, well, it would be a decimal that could be converted to a percent rate of decay each unit of time. 18% decay, actual decay rate per unit time. If you want to make sense out of that, why does that work? Well, just plug in t equals 1. You know, the starting amount was 10. If you plug in t equals 1, 10 times 0.82 is 8.2. The amount of the drug went from 10 down to 8.2. It went down by 1.8 milligrams, which is 18% of what you started with, 18% of 10. That's why it makes sense. Did you catch that? The amount at time 1 would be 8.2. 10 minus 8.2 is 1.8. 1.8 divided by 10 is 0.18, 18%. How much of the drug is left after 6 hours? f of 6 would be 10 times 0.82 to the 6th power. Do the power first, then multiply by 10. About 3.04 milligrams. And by the way, you could get the same answer by repeated multiplication. You could take 10, multiply by 0.82, 1 time, 2 times, 3, 4, 5, 6, and you get the same answer. But it's nice to have an exponentiation function in your calculator so you can avoid doing that over and over, especially if the power was really large. That's how much is left as a quantity in milligrams. If you were asked for the percent decay of that, the amount of decays is 6.96. 6.96 divided by 10 is 0.696, or 69.6% is the amount of decay over 6 hours. Notice this percent decay over 6 hours is not 6 times 18%. That's a tricky thing. Some people think it should be, but it's not. That's not the way exponential growth and decay works. You were not asked for that. That was just an add-on there that I added. Part D, how long until just 1 milligram is in the body? Again, the main application here being maybe, these doses are 10 milligrams, but you're feeling like it's unsafe if you were above 11 milligrams. Now, probably they wouldn't make a drug where it's unsafe just 1 milligram above the dose. But that's the kind of thing we're talking about here. Well, you got to solve for when f of t equals 1. 10 times 0.82 to the t equals 1. You got to solve for t. Use logarithms. For variety, let's use a common logarithm. You might wonder, well, is that allowed? Yeah, you can. When you're solving exponential equations using logarithms, you can actually use any logarithm you want. It will work with any logarithm, though on calculators only log base e and log base 10 are available. Actually, Mathematica can do any logarithm. I won't show you how right now. Just for variety, let's, first divide both sides by 10 and then take the log base 10. Although that is actually convenient here because 0.1 is a power of 10. So it's convenient to use log base 10. Log base 10 of the right side here is going to be nice and simple. What will it be? What do you have to raise 10 to get negative, or to get 0.1? Had a Freudian slip there. -1, right? 10 to the -1 is 1/10 or 0.1. So log base 10 of 0.1 is -1. That's the exponent you need to raise 10 to get 0.1. That's what logarithms mean, or log base 10 means at least. And here we can use property of logarithms. There's another property that says bring that exponent down in front. These are not inverse functions of each other, but there's still a property of logarithms that can be used here. 10 times log base 10 of 0.82 equals -1 on the right side. Therefore, t is -1 divided by log base 10 of 0.82. Wait, how can that be? How could t be negative? Did I make a mistake? Well, it's deceiving. It looks negative, but it's not. -1 is negative, but log base 10 of 0.82 is also negative. So you get two negatives being divided, which gives you a positive. Log base 10 of 0.82 is -0.8086. Take -1 divided by that, you get a positive number, about 11.6. So about 11.6 hours after you take this pill or cough suppressant, maybe in liquid form, it takes that long for it to get down to 1 milligram left in your body. assuming this is accurate information. Okay. We didn't have time for theoretical stuff about logarithms like proving log properties. I do talk about that in the lectures, though not at, I don't think lecture 5 I do. It's later. It is probably worth re-emphasizing in here because I do typically put at least one proof on exam 1. Maybe even 2. There are appropriate times for proofs in here, okay? We'll maybe talk about it next week. Have a good day.